Okay, here we are with our last example from geometric series, and now our our common ratio or multiplier. I consider these synonymous, our multiplier or common ratio. Now we have a variable in there, so this is going to get a little bit trickier. Um, well, let's see. We start off. If we're trying to write this as a geometric series, a times r to the n, our a value, that's our initial value, our a value is clearly 1. And then from 1 to 2x, how did we get there? Well, we multiplied by 2x. So in other words, 1 times 2x equals 2x. That gets me to my second term. And my second term, 2x, if I multiply it by 2x again, I get to 4x squared. Oh, my third term. And to get to my fourth term, if I have this 4x squared and I multiply it once more by 2x, here I am at 8x cubed. So my r value is this multiplier, the common ratio. Just to be sort of to give another way of finding that common ratio, if you take the, let's see, if you take a over n minus a plus, sorry, a sub n plus 1 divided by a sub n, you should get your r value. So if we think about that, if you take 8x cubed over 4x squared, we get 2x. And if we take 4x squared divided by 2x, we get 2x. So if you take, a term and the term before it, do some division, and we're getting this constant value, that's our common ratio, that's our multiplier, which says that we can use a geometric series. So we get a is 1, r equals 2x. So we could rewrite this geometric series as the sum from n equals 0 to infinity of 1 times 2x to the n. And we want to know, does this converge or does this diverge? And I'm looking at the question right now, and hold on one second. So we've answered a. The common ratio is 2x. So we answered a. Write the function that gives the sum of the series. So we did that. That's right here. And before we answer C, let's think about, does this converge or diverge? For it to converge, the absolute value of r must be less than 1. Well, r is 2x. So for it to converge, 2x must be less than 1. And for 2x, the absolute value of 2x to be less than 1, x must be less than 1/2 and greater than negative 1/2. And if that's true, then um, provided that x is between these values, between negative 1/2 and 1/2, then my function will converge. So its convergence or divergence is dependent on the x value falling within that range. So given this idea, and we'll play more with this over the next couple of days. Given this idea, we want to say in a single viewing rectangle, graph the partial sum s sub 3. Well, this is s sub 3. It's here's my n equals 0, n equals 1, n equals 2, and n equals 3 term. So if I were to graph what's given to me, that is s sub 3. So I'm going to graph s sub 3. Let's turn this on. And I'm going to go back to function. And what I want to graph is my partial sum. So 1, that's n equals 0, plus 2x, that's n equals 1, plus 4x squared, n equals 2, plus 8x cubed, that's n equals 3. So when I add them all together, that's s sub 3. And it says graph it in a single viewing rectangle graph. So I'm going to press zoom 4. and graph this. Sorry, I paused that to mess around with the window. So here I have, this is S sub 3. Again, that one value is S sub 0, or A sub 0, A sub 1, A sub 2, A sub 3. When you add them all together, that's S sub 3. I changed my window to go from -1 to 1. And I want to look from -1 to 1 because what I found is that my S sub n should converge when x is between -1/2 and 1/2. And I want to sort of illustrate what that looks like. So in other words, for x values in between -1/2 and 1/2, this, go to y equals, this approximation of S sub n, this is just S sub 3. There, as n approaches infinity, there'd be infinite more terms. But here's an approximation for S sub n with degree 3. In other words, this graph here, when x is between -1 and 1, -1/2 and 1/2, this graph should level off. It should approach a single value because we know that for these values of x between -1/2 and 1/2, my function converges. And for all other values of x, my function will diverge. So if I graph this, given this window, if I graph this, notice that this is about x equals -1/2. Here's x equals 1/2. For these values, the function is flatter, not perfectly. As n gets bigger and bigger and bigger, it would be better illustrated. But the function is much flatter, and that means that in these values between -1/2, x equals -1/2, and x equals 1/2, my function is actually approaching something. And let's try to illustrate this even better. Let's add. Ooh, let's add some more terms. So 8x cubed becomes 16x to the 4th plus 32x to the 5th plus 64x to the 6th. Let's do one more. Plus 128x to the 7th. So what I'm doing is I'm getting a better approximation for as n approaches infinity. And when I graph this, we see, -1/2, it steeply declines to the left, meaning the function diverges. And for all these values here, my function is approaches a single value. And then after x equals 1/2, my function goes up, up, up infinitely, diverging. So in this region between -1 and 1/2, -1/2 and 1/2, sorry, my geometric series approaches a value, whereas to the right of 1/2 and to the left of -1/2, outside these bounds, that sum diverges. All right, so that's it for this. Some big topics, and we'll take some time to wrestle with this.